All right, let's talk about some important things that might go wrong in trying to apply the mean value theorem. Whether they're physical or not, we'll think about later. So here's a setup of the mean value theorem. Suppose we know that we started here. You don't always have to start at 0, 0 for the mean value theorem, but we're just trying to make the arithmetic easy. Is there a way we can draw a position function from here to there such that it never has a slope of 8 meters per second? So think about that. Well, one way you could do it is you could go at a certain speed for a while. Are you ever going 8 meters per second on that line? Well, its slope is not as steep as 8 meters per second, so this might be 6 meters per second or 5 meters per second. And then go some other speed and have this be a sharp corner. So here your speed would be greater than 8 meters per second because the slope is higher than 8. Here it would be lower. So we're asking you to instantaneously go from running like 6 meters a second to 9 meters a second without passing through 8 meters a second. That's a good trick, right? Not very physical. That would require infinite acceleration from 6 to 9 meters per second. So the problem here is that the derivative does not exist at that point. So if you have a function like that, which is hard to do if you are trying to do physical acceleration, but there are functions where you have like a line and then another line. Those would not work for the mean value theorem because f prime does not exist, and that's kind of where we would hope the slope would be exactly 8 meters per second. But it's not precisely defined. You could say there isn't just one unique tangent line. There's a bunch of different tangent lines there. So that's one way that the mean value theorem wouldn't apply if the derivative failed to exist at least one point. Another way to do it would be to say, well, let's say you're running 6 meters per second, and then you're still running 6 meters per second. Notice both of these line segments are less sloped than our 8 meters per second. And let's say this was an open circle and that's a closed circle. So the person was running 8 meters per second, 6 meters per second for a while, and then 6 meters per second again the whole time. What happened here? I would call that teleportation. They went from like, I'm not being picky about the numbers here, but let's say this was at maybe 3.5 meters, and then all of a sudden they were at 7 meters a split second later. That's a good trick. If you can do that, come talk to me and we'll find ways to make lots of money. But there's no way to find a point on the x-axis where the slope of the position function is 8 meters per second. So the problems here, this one, the function is not continuous. It can't be drawn by keeping your pencil on the paper without lifting it up to jump somewhere. And this one, the function is continuous, but it's not differentiable. Differentiable means it has a derivative at every point in the interval. So we say f is not differentiable. In that interval. So we're not saying it never has a derivative in that interval. We're just saying that there's at least one point where it fails to have a derivative in that interval. So the mean value theorem needs the function to be continuous and differentiable. Now there's a slight difference. You need the function to be continuous on the overall interval closed and the differentiable on the open interval. So I'll say see the book for details. We won't worry about that too much. Here's another question. What if I had the same diagram but my curve went something like this. Does the mean value theorem still apply? Is there ever a time on this curve where the slope of the tangent line is 8, or whatever the overall average slope is? Well, yep, it works here, and somewhere here, and somewhere here. Does that break the mean value theorem? Well, the mean value theorem said there is a time, or at least one time. It didn't prohibit there being more than one time. So we can say, okay, to have multiple locations where the derivative matches the overall average rate of change. So here, here, and here, those all work, and that doesn't break the mean value theorem. It doesn't contradict it.